Hello and welcome to our talk, how to migrate 100 clusters between clouds without downtime. My name is Manuel Stößel. I'm a systems architect and tech lead at Kubermatic. We're doing a whole bunch of Kubernetes and cloud native consulting, and we're developing the Kubermatic Kubernetes platform, as well as Kube1, our Kubernetes management tools. With me today is Tobias Schneck, head of professional services at Kubermatic, and he's going to tell you a few words about himself now.
Yes, thanks, Manuel. My name is Tobias. I'm already working 2.5 years for Lutze and mostly responsible for professional service, where we discovered a way how to migrate clusters. So this was a fancy idea, and now we want to present you how far we came to the journey. And so handing back to Manuel.
All right, thanks. Right, why would you actually want to migrate clusters between cloud providers? And there are actually a couple of reasons for that. On the more businessy side of things, you might have better contract conditions at another cloud provider, so you would be able to save cost. There could be the need to migrate data centers to a different hosting provider or cloud provider from a logistic point of view to like a legal point of view, or you're driven by a multi-cloud strategy and you want to decrease your dependency on one single existing cloud provider and expand out to other providers. There are also some technical reasons for that. So again, more a logistical kind of reason might be that you have a location migration of a data center, or you might want to migrate to another network segment for separation of concerns or other reasons. You might be adapting improvements in your on-prem and cloud environments at a new provider that you want to use, like new features, new different infrastructure technologies you want to use at a new provider. Or you're bound to some constraints when it comes to data location of certain services you're running, maybe on some cloud offered services. For example, where you run your machine learning and where you have your machine learning data, or some GDPR compliance needs that you need to fulfill. So what are the main challenges around moving to another cloud provider? Kubernetes itself abstracts infrastructure, but it does have several kind of dependencies nonetheless, right? So it does consume infrastructure resources. For example, the virtual machines where the cluster itself runs on, it uses and consumes the network provided, right? The IP address space, routing and firewalling rules, management of ingress and egress traffic, and also DNS, as always, and external storage systems. Then there are Kubernetes components that are actually dependent on a certain cloud provider. In most of that is the Cloud Controller Manager that contains the node controller for updating Kubernetes nodes, the service controller, which translates a service type load balancer within Kubernetes to an actual cloud load balancer in the cloud provider's environment, the route controller, which is responsible for setting up network routes in the cloud provider's network. But there are also things like storage classes that map to cloud provider specific storage offerings. And sometimes the overlay network you use has some dependency on a cloud provider as well. And just to remind ourselves, a quick overview of the components of Kubernetes. The central one being the API server, which kind of handles all the changes in state of the cluster itself, and the worker nodes with the kubelet, which runs the actual workload that users run on top of that cluster. And between the API server and the kubelet, there has to be a two-way communication happening. And between the kubelets as well, between the worker nodes as well. And that is one main challenges we're kind of solving today to enable this ways of communication. And that directly leads us to our actual dependencies when we migrate. So for us, the application workload has the highest priority, but we need to ensure, for that to be the case, we need to ensure fundamental networking rules that Kubernetes expect to be in place. Those rules are that all containers within a pod can communicate unimpededly on layer 4, so TCP UDP. All pods can communicate with all other pods within the cluster without netting, and all nodes can communicate with all pods and vice versa, also without netting. And the final one, the IP that the pod sees itself is the same IP that others see the pod as. And this is really important to keep up so that the actual networking between pods and applications works. We have to have some external dependencies that need to be reachable, right? Like externally routed IPs for load balancers and node pod services within the cluster, and DNS names need to be reachable / resolvable, right? And storage. Some applications might have to have state that needs to be migrated without data loss. So when we look at that now, at a level of like scale of hundreds of clusters, maybe, we look at large organizations running a whole bunch of clusters in different locations for different organizational units in different time zones, right? And for those users, cluster users, the cluster itself is just a service that they consume, right? And that means that the cluster connection and secrets, so the actual interface that the user has to the cluster is not allowed to change, right? Otherwise, it would impede the actual service that those users consume. So how do we solve for that? The status quo is we'll have a multi-cloud setup with the Kubermatic Kubernetes platform, our open source Kubernetes management platform. And it has a concept of a seed cluster that holds the containerized control plane of the user clusters. The user clusters being the Kubernetes clusters that are managed by KKP. The worker nodes itself are provisioned via the Kubermatic machine controller, which is a cluster API conform operator that translates a machine deployment object into actual machines, VMs on cloud providers. And we'll use Canal as our default overlay networking, which is effectively Flannel, VXLAN overlay networking with a Calico network policy plugin. And the target is that we migrate the user and seed cluster control planes and worker nodes to a different cloud provider. We'll keep all the external cluster endpoints stable. That means the control plane, Kubernetes API server endpoints, and the actual application endpoints being the DNS and ingress routing. Out of scope for now is the storage replication. The assumption is that the actual application layer manages the storage replication like etcd, which is a feature that we will use to migrate the user cluster control plane. So how does it look? We have a Kubermatic installation that has a seed cluster, which is also just a Kubernetes cluster running in the Google Cloud. And it hosts a couple of user clusters, and we'll have a look at the vSphere user cluster that runs worker nodes on a vSphere cluster. And we want to move all of that over to AWS because for whatever reason, we want to run on AWS. And just some recommended prerequisites doing that in production. You'll have to announce a maintenance window and block cluster updates so that those don't interfere with the actual migration process. We'll have to ensure that our backup and recovery procedure for the seed and user clusters, but also for the application workloads, works, is tested and proven to be working, right? We'll should create a target cloud cluster as a reference, in our case an AWS cluster, just so that we can copy and paste some stuff over. And we'll have to ensure that we actually control the DNS entries and be able to switch over DNS entries to the new cloud endpoints once we migrated the workload over to the new cloud provider. Yeah, and now we'll look at the actual solution approach, and Toby is going to give us a quick demo on how that works.
Okay, then over to me. Thanks, Manuel. Let me share my screen. Hopefully you can see it now. Um, and yes, so what is the solution approach? Um, so first of all, we want to migrate the user cluster workers. So in this case, we want to migrate it and we want to have new workers in the target cloud. How we can reach that? So we're using the so-called machine controller in Kubermatic and Kubernetes, and this controller can create workers based on CRDs, what's called machine deployments. So machine deployment is similar like the deployment of pods. It's a deployment of machines. And if we like change that machine controller and give them a new specification, we can create the machines in the new cloud. What is needed to ensure the traffic is reachable? We need to somehow need a way how to communicate between pods and pods and nodes to nodes. For that, we create a VPN overlay by a daemon set and route then the traffic of the CNI, in our case kernel, through the VPN network. And that's ensure that we have maybe different network segmentations, but still can talk to each other if we have this client-to-client VPN traffic enabled. And uh, at least we should ensure the reachability. That means that we try as long as possible to keep the ingress endpoint stable and then transfer the workload to the new cloud. And after the workload is the new cloud, we delete the connectivity. Okay, how this can look like. So we have the seed cluster what hosting the containerized control plane. Here we have some controllers and we have the Kubernetes containerized control plane. We have there per default a VPN server. This VPN server is used for VPN traffic between this control plane and the workers at Kubernetes. So that workers can connect with the control plane and the control plane can back tunnel the kube control logs and exec calls over this VPN tunnel. Also, we have a machine controller which is configured to place on machines on the vSphere cloud. And we have between the vSphere workers, we have an overlay what's based on kernel. And we have a metal LP service what creates then the inbound traffic load balancer to the dedicated application ports. First step, how to migrate is now to deploy a VPN daemon set. This VPN daemon set ensures that we have a VPN client at every worker node. This opens in the worker node a new interface, and we route the traffic from the VPN interface through the VPN interface, our kernel, to our dedicated overlay. So, and for that, we need to pause the cluster because our cluster is controlled by a cluster controller, and this cluster controller would then reconcile the machine deployments and the VPN servers. So to ensure that this does not happen, we pause the cluster to make some patches there. Next step is after we have the credentials for the new cloud adapted, we can update the cluster spec and specify the new AWS cloud. Then the machine controller get updated and we get a new machine controller instance that can now talk to AWS. New nodes get created and also joins our VPN network and joins so also the kernel overlay routing. The cloud controller now ensures that we also have a new AWS LB what get created. Currently, this LB is not routed, but anyway, the traffic goes from here to over the metal LB service to the dedicated workload. After this happens, we can remove the workload from the old workers and move the workload to the new applications. After this is done, we can also rename the DNS names to the new cloud load balancer and ensure that we have now migrated traffic to the new cloud. At least then clean up the old resources and we removed, we not needed any more VPN overlay because this two workers can now talk to each other with ETH interface. And that's how we migrated it. So to give you a short insight, short look what already is happening, we create a demo. be aware that currently this project is like not fully finished, so it's more a proof of concept state. So as we see here, we have here an app, or what is our reference echo service, and this deployed on a cluster. Let's take a look in our Kubernetes control plane. And in this control plane, we have the dedicated clusters here. So first, we have here this kubecon migrate cluster, what we want to migrate. Here we see this cluster contains the containerized control planes, a machine deployment of 2 nodes, and a so-called echo service Nginx and metal LP. This metal LP points to the IP address of the vSphere and deploys our echo services. So if we go to the vSphere, we see here under the cluster ID, what is here KBHC. We see here the virtual machines running. And this one we want now to move to the AWS. First step, what we already did is that we deployed a VPN. So we patched our VPN server. And for that, we see that we have a cluster spec and we have so we see here also in our C cluster that everything what you see in Kubernetes is also represented as a cluster CRD. In the cluster namespace, here, this namespace, we see the control planes. And here you see that we have like the OpenVPN server running, and we have the API server and all other components running. If we connect here to the user cluster, so let's take this shortcut. Yes, I want to go to the kubecon cluster. We see a bunch of containers here, and we see here that we have our echo service, we have our Nginx, we have our kernel, we have our VPN client. And that's now what we want to migrate. So yeah, first step is the VPN is already there, so we can now deploy our control plane and migrate it. What is, I think, the most interesting part of the whole thing. So we can then say, okay, here our update target cloud script. What does it do? So we have here, yeah, first we need somehow the cluster ID, and we need the project ID. The project ID we find here in our Kubermatic URL here, the project ID. We can copy it and we can here place it. So what is the first step? We create a backup. That's the backup of the specification of this cluster. So yeah, I want to create it. And as next step, I want to pause the cluster. And yes, after I pause the cluster, the controller does not care anymore. So now I can safely update my cloud provider. So yes, I want to patch the cloud provider. So I create a new cluster YAML, what we now can take a look on. So if we go now to my files, I see here that I have here under control plane somehow a new file. Where it is, should be here. Let's see. Okay, yeah, here we are. Now we have one backup cluster YAML and the patch YAML. So let's see what's the difference is. So yeah, so currently that's our cluster CRD. On the left, we have the backup cluster spec, and we have here our API server token and so on. And we have the finalizers, what clean up our cloud when we delete the clusters. And that's now the important stuff. We have here the vSphere configuration, what reference a credential and the folder and so on. And that's something what we now remove, as well as the status fields, and we apply this change now to our cluster. And the first step to remove the credentials, this is needed. So let's apply that and see what happens. So we see now we have configured, and now to start reconciling, we need to unpause the cluster, that the cluster controller can take care about the change. And yeah, let's see what now is happening. So we have now the cloud spec, what get recreated by the cloud controller. So hopefully everything works well. And we see that the cluster get now reconciled. Yeah, we see now we're getting the new object. We have the vSphere is empty. Okay, this looks good. And we can now watch that hopefully, yeah, we see the API server is reconciling to now an empty cloud provider. Okay, cool. That was the first step. So now as next step, we want to change to our AWS. So let's go out of this view and let's pause the cluster again. Like currently, depending on the Kubernetes controller, we need this two-step upgrades because we are just a kube control client and not an operator. And now we can patch the cloud provider. So what happens now? Yes, I want to patch it. Yes, I want a new secret. So there we create a new secret reference for the AWS credentials. And then we created a new cluster patch file again. So let's also see here what's different now. So we see now we have changed, basically removed the finalizers because these are not valid anymore. We added annotation here to the Kubernetes AWS region. We patched cloud spec AWS with the credentials, and we have a migration, a new data center. So that's the new migration data center where we want to migrate it. After we now make that pause to false, the controller try to reconcile where new AWS should place there. And the nice thing is, therefore, Kubernetes creates now a new security group, a new roles, and that's hopefully what's now happening. So let's see. So let's patch that cluster and configure it. And yeah, now let's unpause the cluster and see what's happening. Good. So, okay. So what we see now here, we can reconcile. We see we get now here also an AWS data back from the Kubernetes controller and see what we created, new security group and an instance profile. Cool. So let's see what happens with my components. We now seeing, yeah, we have a restarting API server again. It started now with the new cloud credentials. So let's try to find a little bit out what's happening there. So we have here a deployment. So, and let's take a look into, oh, that's the wrong side. Let's see what we have placed there. So get explain deployment. For sure, I need to write kubeconfig. And now we should go to the API server of our cluster and see that here we have specified, hopefully now, the cloud provider with here our new cloud provider AWS. And now that's reconciling take place. And we also have a new machine controller that now is able to talk with AWS. So what we can now create is the new AWS workers. So let's go back into the user cluster. So yeah, here go to this kubectl migration cluster. And first, yeah, pause all machine deployments to be sure. So worker machine deployment pause. That we don't upgrade this all machines. And yes, pause, done. And then we can now create our new AWS workers. Therefore, we need first a few inputs. So here we need to specify the cluster ID, the instance profile, and the security group that Kubernetes had created automatically. So here, yeah, I want to see the metadata. We have here the cluster ID. So let's change that one here. We have the AWS instance profile. What have we created? What should be that one? And we have the AWS security group. Okay, so let's create that one. Save it, and then running the script deploy. So now, hopefully, fingers crossed, we create new AWS workers. So yes, I want to create one. Here we see that's now rendered in the machine deployment. We see our security group. We see that we want to have a T3 medium, and yeah, that in the US West 1 C zone. Okay, then let's deploy that. So fingers crossed. Yes, as has been created. So I want to watch the creation. Yes, I want to see that. And we now see what the machine deployment. We have a new machine deployment with Ubuntu Target AWS. What creates 2 new machines, and what get provisioned now in AWS. So let's see. Our workload is still running, as we see. We have here our target cluster. We see also here we have the new Ubuntu Target AWS node group, what's now get muted. Yeah, let's go to AWS and see what's have been created. So here, hopefully the AWS console is fast enough. We can now go to the EC2 instances and should see that we can have booted now new 2 instances. And let's see. Yeah, we see here initializing. So that's the new 2 machines, what we created. If we take a look here, we also see the tag. That's the cluster for what we have. And for that, so we have created new machines. So let's wait until the point they are get booted. In the meantime, we can take a look in the load balancer. So hopefully we also have a load balancer created. That's what the AWS Cloud Controller Manager will create, because we already have a service type load balancer in the cluster. And that AWS takes over and creates also a load balancer on their side. So let's see, that's not the right one. That's the right one. Here we see there's a cluster created, but we don't have any instances here because, yeah, the instances get now booted. So let's go back and see how fast they are coming up. Okay, we now see that we get a new node that's not ready, but we can already connect to him. So let's try to SSH into one AWS node. And let's go here for that kind and see what's happening there. Yes, I want to connect. And yeah, we see here that we have here a flannel route, and we will soon have a kube interface for the VPN server as soon as that's started. Here we go. Here we see that interface, and we can now try to get the interconnection between one cloud to another. So I then connect here to the on-premise node on the down, and let's connect to that one, Ubuntu, and test if we are now can talk between clouds. Here as well, I have IP address for the kube interface, what is 10.20.42, and let's try if we can ping it from our AWS node. Okay, now we see that we get a connection here from the cloud node to the on-premise node. Good, cool. So next step, what we now need to do is to migrate our workload. Okay, cool. Then let's go back here and here as well, and try to migrate the workload. So we have now switched here to the user cluster to see what's happening and to see, take a look in the echo server namespace. Sorry. We see now here, okay, the echo server is deployed on the migration vSphere node. We want to now to roll out the new workload to the new cloud. So let's try to cordon the nodes, because that new workload should not anymore go to this old nodes. Good, let's cordon, and we have the another node to cordon. So that means that the node should be now marked as not schedule able. Yes, so scheduling disabled, perfect. So we can now use the kubectl rollout restart feature to now restart our deployment of the echo server in the namespace echo server to trigger like a rolling release of the echo server without any change. So yeah, let's trigger that one and see what's happening. In the down, we see, okay, that's still, we have the application up and running. And yes, so now we see the container get created in the new cloud. So first success. So hopefully this will now work. We see that now a new container is running on the new AWS workers, and we can now terminate the old one. So that's it's now going step by step, and we have 3 new workers. And you see the service is still reachable, and we get now hopefully also, if we go to the browser, we can see here detail that we get back from the AWS node to cause. So we have, where is the host name? No, it's just the host name. We see that the workers are running in the new cloud and still reachable through our old endpoint. Cool. So that seems to work. Like now, the next step would be to migrate all other workload to the new cloud, remove the load balancer, and then using the new DNS name. So we can quickly try if the new load balancer is now listening. So yeah, we have here the new instances, and maybe the DNS name is already propagated. To see if this is working, we can see, okay, let's change that to the new DNS name. And no, so DNS is not there. So yeah, good. Then finally migrated to the new cloud. So how are the next step looks like? So that's how we can create the migration, the worker user clusters, and to move completely to another cloud, we need now to migrate also the seed cluster. For that, how we can achieve that is the same way. We're reusing the same principle. So here we have the workers now in the new cloud, and now we need to migrate control plane. The good thing is on that, in any case, the workers workload is still safe because it's already in the new cloud, so we can migrate it even if we may break it. The only thing what would maybe not work is an upgrade of the Kubernetes, but still the workload is safe. So how we migrate the seed clusters? First, we create new master nodes for the seed masters. So that means we creating new nodes, putting a new Kubernetes API load balancer on it, update the API endpoints because this API endpoints are stable in the Kubernetes cluster. And then we block for sure the seed cluster for upgrades so that we don't anything trigger unexpected during this migration. And then, yeah, we migrating the user control planes in the same way as migrated the workload now at the user clusters. So we move the etcds to the new cloud and using etcd quorum for the data migration. And yeah, for sure we should have backups and recovery for all the components. How does this look like? For example, here we have our seed DNS for our own API server, what's pointing to 3 masters. There we have now our AWS clusters hosted the control plane, and we have the workers who hosting the containerized control plane, everything on GCP. Then as first step, we would again place the VPN, that time in the seed cluster, connecting every worker node and master nodes, then create a quorum with 5 etcd for the master nodes. That ensures that the new 2 etcds get the data replicated from GCP nodes to the AWS nodes. Then, as next step, if we have achieved that, we can remove 2 GCP workers and still have a quorum of 3, so 3 of 5 if enough is enough for the quorum. And we can therefore also change now the DNS name to the new AWS cloud provider load balancer. So there now we can then remove the quorum also from 5 to 3, and we have a stable control plane. For sure, also in this procedure, we need then to clean up, remove the old GCP node, again, create a new AWS master node, and then we have 3 etcds healthy in the new cloud migrated. In the same way as we migrated the user clusters workers, we now need to migrate the C cluster workers. For that, we here can change the VPN again, create a new worker nodes, and then in this kind also changing here the cloud provider here that it's pointing now to AWS. After this has happened, we can increase here in Kubermatic settings the default value of etcd replicas to 5. That means that the Kubermatic user cluster controller manager creates 2 new etcds for every user cluster. That ensures in the same ways as we migrated the etcd on the top, it's migrated also for the users cluster. So I have now a quorum of 5 etcds running, still pointing to the old DNS, but between clouds. As next step, we now creating a new cloud load balancer and rename the wildcard. So that's the connection from the user cluster workers, what we already migrated to the new cloud load balancer. And yes, then we switch over. We adding one new AWS node, replacing all GCP nodes. So we have then a quorum of 3 etcds per user cluster on the new cloud. That is the most reasonable target. So now we are safe and we can remove the old missing worker nodes, clean up the old cloud resources. That means we scale down to etcd level 3. We remove then the VPN overlay, and we now have the kernel overlay what's routing between the workers, again between ETH0. So then we are successfully migrated every user cluster in the seed cluster to the new cloud. So that is the approach what we think is possible to migrate really 100 clusters without downtime and in a scalable way. So for sure, we are not right now that we just press a button, but that's our future target. So we want to automate also the cleanup procedure. And for sure, if you want to really make it scalable, we need to write an operator. Currently, we did everything by a hacky bash script. And to not doing that by hand, the health checks, we need to have an operator who check the health check, the conditions, and have also some repair options and retry options. But therefore, the Kubernetes reconciling pattern match in the same way as match for our cloud migration, where the Kubernetes controller creates the new cloud provider and so on. We can use the reconciling also for the migration and using, okay, we have a new target cloud operator, take care about that, matching the old state to the new state. Technical, we also need to stabilize the VPN connection. So right now we have only one VPN server. This could be maybe on a bottleneck on bigger clusters. Maybe we should deploy multiple VPN clusters, and we have maybe have also more soft switch between VPN and host networking overlay. That's something what we need to explore more. And maybe their Wirecard can be an alternative as a VPN connection, what could help maybe on the setup. Okay, one more detail. Yeah, currently we tested it in 1.17 seed cluster where the managed fields feature is not included. Somehow this makes a little bit of trouble between, okay, you have an like patch by kube control and you have an operator what reconciling the fields. So that's why currently I'm a little bit limited on the 117 seed clusters. As you saw in the demo, the user cluster can be on 118. Cool, then yeah, thanks for your attention. We are happy to answer any questions, so feel free to reach out now. And yeah, thanks to listening. And yeah, Manuel, few last words from your side.
No, that was amazing. Thank you so much. And we're open to questions now.
Okay, thanks a lot, and looking forward to your questions.